In humans, the ABO blood group and the rhesus factor blood group are under genetic control. The inheritance of ABO is controlled by one gene, of which there are three alleles, A, B, and O. The alleles A and B are codominant, so they're equally expressed in the phenotype, and the allele O is recessive to A. So that's only expressed if it's homozygous. There are four phenotypes, A, B, AB, and O. Then we've got onto the rhesus factor, which is another gene where capital R is dominant to the rhesus negative lowercase r. The genes for the blood group and the genes for rhesus factor are not sex-linked and they're not on the same chromosome. Figure 3 shows the phenotypes in a family tree. So, number 2, we have to give the genotype of number 2. Do not include the genotypes for the rhesus blood group. We're only looking at the ABO blood group. Okay, so this one is AB, and you've got 2 copies of each gene, and these are codominant, so number 2 has got to be AB. Okay, number 1, this individual is blood group A. Now, because blood group A is dominant to blood group O, they could have that genotype or they could have this genotype. Which one have they got? Well, now we have to look at the offspring. This offspring, number 3, is blood group A again, so we're not entirely sure whether this one is homozygous for A or heterozygous for A and O, whereas blood group B must have a B from this parent and an O from the other parent. So therefore 1 has to be AO. So if you can't determine what their genotype is, look to offspring. Give one piece of evidence from figure 3 that the allele for rhesus positive is dominant. Whenever we are asked these questions, we always look for parents that have got it and offspring that don't. So you'd say that 3 and 4 are rhesus positive. I'll just check that. 3 and 4 are rhesus positive, and whereas they have offspring 7, 3 and 4 are rhesus positive, whereas 7 is negative. Therefore, 3 and 4 must be heterozygous. Okay, calculate the probability of individuals 1 and 2 producing a rhesus positive son with blood groups A, individual 3. You can assume that 1 is heterozygous for rhesus blood group. So number 1 is a male who has blood group A and they are rhesus positive, and they've said we can assume that it's heterozygous. So the full genotype, including the 2 genes of number 1, is A, O, capital R, little r. Okay, now the mother is rhesus negative, and we've been told that the rhesus factor is dominant, so she must be 2 recessive alleles if she's negative, and she has blood group AB, so she's going to be AB. Okay, so we're looking at a dihybrid cross. So let's have a look at the possible gametes. So we've got A and an R. A and capital R is one combination, or we can have A and little r, or we can have O and big R, or we can have O and little r. And so there's 4 different gametes that we can have for father. The mother's gametes, she's going to have A and little r, or B and little r. Makes this a little bit easier there. So it's a dihybrid cross. That we need to calculate. This one's A. This one is A, little r, A, O, big R, little r, and this is A, O, little r, This one is A, B, big R, little r, A, B, little r, B, O, big R, little r, and this one is B, O, little r. Okay, so what are we actually looking for? A rhesus positive son, so at least one capital R, and blood group A. So let's highlight the ones that we can see if that applies to. So blood group A and at least one big R we've got here. That's not one big R. Blood group A we've got here. Any more? Big A. That's AB, B. So we've got 1, 2 out of 1, 2, 3, 4, 5, 6, 7, 8. So we've got 2 out of 8 is the proportion. So we'd simplify that to 1/4. Okay. Now, which is 0.25%. 1/4 is the probability, or 25% is the probability that they will have a child with blood group A who is rhesus positive. But we're not looking for a child, we're looking for a boy. And there's a 50% chance you'll have a boy or a girl. So all we need to do with that is we need to half it to get the probability of a boy. So we divide that by 2. And that gives us 12.5%. Okay, the next one. Scientists determine the frequency of the ABO alleles in phenotypes in a large population. They used a statistical test to determine if the frequencies differed significantly from the frequencies expected according to the Hardy-Weinberg equation. The frequencies of the individual alleles were 0.15 plus 0.65. So if there's only 3 alleles in the whole population, then the frequency of the B allele will be the frequency of the A allele plus the O allele, and subtract that from 1 equals 0.2. Okay, finally, name the statistical test to determine if the observed frequencies. That should automatically make you think chi-squared. How many times an individual falls into a particular category, and then comparing those numbers with how many you would expect, that is chi-squared. Number of degrees of freedom is the number of categories minus 1. Okay, so that is 2. Number of categories is 4, sorry. Number of categories is 4, so there's the A blood group, B blood group, A, B and 0, and O blood group. So 4 categories minus 1 equals 3. The scientists concluded that the observed frequencies of the 4 phenotypes differed significantly from the expected frequencies. So basically saying that Hardy-Weinberg is not true. And remember those conditions where Hardy-Weinberg had to be true. You had to have no crossing over, no random mutations occurring, no emigration, no selection pressures in order for the allele frequencies to stay the same. So if the allele frequencies or phenotype frequencies had changed, then these are the reasons why. So there was emigration, mutations to produce new alleles, selection pressures, for example. So that is how you could score full marks on question 6.